Hi, I'd like to welcome everyone to today's ADAPT webinar. My name is Spencer Lee. I'll be conducting the webinar today. Some of you may have been in the webinar yesterday where we covered the design of a PT two-way slab frame strip using ADAPT PTRC, which is our 2D software. Today we're going to cover design of a single level PT slab in ADAPT Floor Pro, which is our finite element software. And some of you have used that software, some may be more familiar than others. So we're going to start at a pretty basic level in terms of building the model, modeling support lines and design strips, modeling tendons, and then evaluating the slab for considerations relative to PT design, for example, pre-compression, balance loading, and allowable tensile and compressive stress. So I'll make just a couple of announcements. If you have any questions, you should have the ability to type a question into the question box. I'll answer questions as we move through the webinar, so long as the answer can be brief. If it's more of a detailed answer that I might have to respond with, I may ask that we just wait until after the webinar, and then I can email you or contact you to respond to that. If you have any questions related to specific models that you might be working on or troubleshooting type issues, then we can answer those also outside of the webinar. And you can always contact our support staff at support@adaptsoft.com. The webinar will be recorded and will be available for reviewing on our YouTube channel, which is youtube.com/adaptsupport. And if you go there and select the playlist Adapt Webinars, we put all of our webinars on that YouTube channel for your playback. So we'll go ahead and get started. On screen you should be seeing a CAD file just of an oval shaped slab. This is the same slab we looked at yesterday. For those of you, it may look familiar. So we're going to take this slab, and the slab is obviously not a typical or common shape. It's not super complex, but it does add some complexity and some decision making in how we're going to set up the design strips. So one other note, today we'll be working in US units and ACI code, so I apologize for those that might be more used to working in SI units. So we'll go ahead and start. I'm going to close this slab. Just a couple of things. We have some walls, columns. We have a column located here, which adds a little bit of, again, complexity, decision making, and how the design strips will be laid out. We're going to assume that the banded tendons are going to be placed in the X direction, and and you can see I'm highlighting basically the shape, the layout of the banded tendons, and then the uniform tendons will be in the Y direction. So this is our assumption. This is how we're going to lay out the post-tensioning in the slab in this case. So let's go ahead and close the CAD file. In order to import the CAD file into Builder, I have to have the CAD file closed on my end. So we'll go ahead and do that. And today's model will be built using a CAD import, transforming some of the components into structural components in Builder, and then for the others we may have to trace to build the slab. So ultimately what we're going to end up with is something like this. And if we carry that further, this does not have any tendons in the model. If we carry this out further, we're going to end up with something that looks like, let me go ahead and open one more model here. So this is ultimately the model that we have that we're going to end up with. And this model has banded tendons and uniform cables. The uniform cables in this model are a little bit different than how we're going to model uniform. In this case, we space them every 4 or 5 feet. We keep the spacing consistent within certain zones of the slab, and then we just adjust the number of strands. So we can scale that up to 2, 3, 4, 2.5. You can scale it up using or down using decimal input also. So we'll talk about that as we get to this point. But for starters, we'll go back and just go ahead and start from scratch. So the first thing we'll do is when we open Builder, we don't really need Edge. Edge is used as our multi-story engine. So because we're evaluating the slab in Floor Pro, which is just single level design and evaluation, analysis, and so on, we really only need Floor Pro. You can still build a multi-story model in the software with only Floor Pro and Modeler. Modeler is always turned on, but if Edge is turned off, then you don't have the ability to analyze the structure as a multi-story frame. Again, that's not needed or necessary for this training, so we'll go ahead and just limit this to Floor Pro. I'm also going to make sure that I have the design scope set to RC and PT. RC and PT gives me the ability to really do a hybrid type of a slab where I can model support lines that are set to the design criteria relative to an RC design versus a PT design. So this is all-encompassing in terms of PT modeling and just regular conventional slab modeling. We're going to leave the strip modeling option turned off. Some of you may have used this before. This allows us to export strips to adapt PTRC. It's a nice tool to have if you might have don't have a lot of experience with design of PT slabs and you want to just get a starting point for what the post-tensioning should be in your model. However, it is limited, so it works well with let's say prismatic slabs where you don't have a lot of changes in thickness and different drops and steps. But once you get into more complex slabs, it becomes harder to use this tool. And frankly, this tool is going to become less and less needed in terms of designing inside of Floor Pro once we release the new version next month, which will include an optimizer that's similar to the PTRC recycler, that it will allow you to optimize groups of tendons and spans very easily. So, and if I get time, I may show that. I will note also that if we run up on time, time crunch today, we may schedule a second session that is a continuation of this tutorial that we'll be working on today. So go ahead and launch the program here. And the first thing I'll do is just save this file. So we're going to just save the file, give this file some name. I'll turn off some of my toolbars. I'm not going to go through each and every tool that I'm using just for the sake of time, so we're focused more on the process versus every tool that we're using. And if you do want to open a toolbar, I'll make this comment, and you can always go to User Interface, launch the toolbar, or right-click in this gray area here and launch the toolbar. So the first thing we want to do is we want to build the model. In order to build the model, I want to import a CAD file. We could also import a Revit model or an ETABS file just to get the geometry and the slab modeled, but this is a pretty common way of just doing single level slabs. So we'll import this CAD file that we have available to us. And let's see. So the slab is here, and when we import the CAD file, we have three different options. The first option is to calibrate, and you almost 100% of the time need to calibrate the model. If you don't, then you're going to end up calibrating after you've imported. So we're going to calibrate, and that allows us to scale the model or the CAD file into our interface. So we have to set a scale for a given dimension. It could be a column edge or a wall length or a wall thickness or a given set dimension. If you bring in grid lines that we know, something that allows us to scale is necessary. We can also move the slab into to an origin. So if we wanted to set an origin for multiple CAD files that we're importing, then we would move this into position using this move option. So I'll go ahead and move the file as well. And then lastly, if we've already defined levels in our model, we have the ability to then insert the CAD file at a specific level. So by default, the program assigns 3 levels. There's a current plane, there's a bottom plane, which would be the supports, and there's a top plane. And you can see here that the current plane that's shown in this list is bottom plane. But the plane that I'm currently working on that's active is actually current plane. So if I don't select this third option, then everything is going to be imported to the active plane that I have selected, which is current. If I choose to use this third option, then I have to set it to the plane that I wish to import to, which in this case I would change this to current. So I'll go ahead and do that. I'll select this, change this to current plane, and we'll call this CAD import 1. I'll say OK. The program will insert the file, and immediately you'll note that there's a small magnet icon by the crosshairs for the cursor, and that indicates that we're in an active mode. The program is prompting us to do something. And at the bottom left of the screen, you'll see it says enter the start point of the calibration line. So I know that this dimension on this column is 24 inches, so I'll go from point A to point B, and down again in the user prompt bar, we enter the dimension in feet. So this is 2 feet, and I say enter, and now it's prompting me to move this into position. So to get the drawing file back, I'll just first zoom extents, and I'm going to insert this column here. This will be my reference point, my first point, and I'll go ahead and well, I can't select the center of that, so let me just select an edge here that's snappable. So I'll select this point, and I'm going to move that. I can either use this or enter the next point graphically, or I can enter 0, 0, and then the Z dimension is 10. We're on the current plane, which by default is 10 feet above the base level. So we'll say 10, enter, and that moves that point to 0, 0, 10. So this is now our imported CAD file, and now we have the ability to potentially transform the components into we can transform the drawing file into components if we have polygons that allow us to transform. And you can see there are some polygons. Most of the columns here are closed, so we'll go ahead and just select these columns, and I'm just selecting Control and snapping on each of these columns, and then I'll use the option for build, transform, and we'll transform that into a column. The walls themselves are lines, so we're just going to build the walls from scratch. Let me go ahead and transform this one, and I'll go ahead and use the transform toolbar now in order to do this. So that's already open. Let me just bring that down into the main screen here. So I'll select the column and I'll transform that to a column. The openings, you can see these are just a bunch of lines, so we have to basically trace openings, walls, and slab edge. And so we'll go ahead and instead of using the transform toolbar, now I have to use my build toolbar because I'm unable to transform the rest of the components. So I'll go ahead and create my walls. The walls, I believe, are 12 inches. I'll change that to 12 in the property and select the green check. And you'll notice I want to snap to the midpoint, the center point of that wall, so I need to use my midpoint snapping. And now I can go through and build some of my walls. And the snap tools are fairly sensitive, so I don't recommend having every single snap option turned on at once. That usually leads to more trouble than that being actually helpful. So I would only limit it to the snap tools that are let's say, relevant to the operation you're trying to do at the time. So the walls are there. Now I'll build my slab, or excuse me, my openings. Let me just exit out of that. I'll go to opening, and I'm going to turn off the few of the snap tools there, and just draw in my openings. Now again, this process could be much faster if we have transformable entities in the CAD file. In this case, we do not, so we're having to do a combination of both from scratch modeling and conversion from the CAD file. So this right here, you can see this crossing for the opening is outside of the wall face, so I want to move that back. That could potentially end up being troublesome when we go and mesh the model. Usually we either want to model the wall to the center line of the wall, or excuse me, model the opening to the center line of the wall, or model it so that it's flush with the face of the wall. And here you can see this is a little bit misaligned also. This is not to say that it won't work, it's just it will lead to a less efficient mesh in the program. So last opening is over here. And then finally we'll go ahead and model the slab. Now the slab in this case is represented by tiny little segmented lines. The program cannot model, or it cannot convert a circle or an arc or an oval shape that's continuous. So you have to segment the slab. So I'll just go ahead, set my slab depth to 8 inches, that's the default, and I'm going to segment this. So it's going to be slightly rough in terms of its shape, but it'll be good enough for what we're trying to accomplish. If you model to every single point that was imported in the CAD file, then those points are used as leader points for the mesh. So what will happen is your mesh could get much tighter than you may want it to be, because you have, instead of having 20 or 30 points defining the slab using these linear segments, you have 300 points defining the slab, and the mesh is dependent on those points which define these closed regions like slabs, openings, and drop panels, thickenings, etc. So let's go ahead and continue around this loop here. And modeling it using these roughened segments versus every single point, you're not going to lose a ton of accuracy in the model by doing this. So our recommendation is to find a kind of a middle ground in doing that. So you can see those are my points that are defined. I'll go ahead and press enter and exit. Now I have a structural model. And if I go to the view model tool, the rendering, this becomes the model. Notice that the CAD file and the structural components are turned on. If I go to a wireframe, you can see, for example, the crossings in the opening. A lot of times the CAD file being overlaid on the actual model can be troublesome. For example, if I try to launch the slab properties and I click this, it opens a slab in this case. Let me see if I can do this for a wall to illustrate this. Notice that it highlights the drawing lines that were imported. So if you double click on a component, it should open the properties of that component. But many times when you double click, it opens the properties of the polyline or the polygon. But you want to open the properties of the wall. So the best thing in our and what we would recommend is to simply turn off the CAD file once you've created the model. And so once you import the CAD file, if you go to the group library option, that CAD file is imported here in this list. This was CAD import 1. I'll just go ahead and turn that off. You can also unload a CAD file, or you may have the need to purge a CAD file in order to remove some and eliminate some drawing entities that are unwanted in a model. This also helps with, I guess, unbogging a model and kind of maintaining it, the size of the file that you're working with. So we'll go ahead and just turn that off. We're left with our slab, and we're going to copy the supports up. So the best way to copy these up, I'll go to a front view, and I'll just window select these supports using the modify copy move vertical. I'm going to copy these up one time, or I could copy them to a specific level. We have the top plane here, so we'll just copy this up one time. And now I have my supports above and below. Okay, so that's the model that we'll be working with. Now, in terms of the material assignments, we're just going to leave the defaults. The material here for concrete is set to 4,000. Typically, we'd probably use 5,000 for a slab or greater, but we'll leave this at 4,000 for now. We could define material for the reinforcement, the non-pre-stressed reinforcement, the pre-stressing, and then there's also an option here for generic, which we will not use. For criteria, we're going to set this to the ACI 2014 code. I want to make sure that we set up the right bar sizes for two-way slab criteria. All of our design strips will be set to two-way slabs. So for two-way slab, we want to make sure that the cover is proper. So the cover for the bars we'll just say is 1 inch, top and bottom. The preferred size of reinforcement for the two-way slab we're going to say is number 5 bars. For shear design, punching shear, we can also set up punching shear studs or stirrups. We'll use 1/2 inch diameter studs here. We're not going to focus much on punching shear today, but this is necessary if you want the program to design it per your requirements in terms of what type of reinforcement it is and also the size. If we go over to tendon height defaults, the tendon height defaults are comprehensive, meaning they apply to both banded tendons and also, let's say, uniform tendons. So we may have to come back and change this when we go and map banded and then we go and map uniform, depending on where we set the CGs for each of those tendon types. So the first thing we're going to work on are the banded tendons. So I'll just go and change this to 1.5 inches. That's my assumed CGS for the bands. The roundup is 0.25 inches. The roundup is used when the program is changing the CGS for, let's say, balance loading. The program has an algorithm where it will lift the CG if we map tendons to meet a balanced loading range. So there looks like there's a question here. Let me go ahead and answer that. The question is, typically construction process is to build a floor and then post-tension that floor and then continue with the next floor and so on. Why is it necessary to model second floor columns? Is there a situation where they need to be modeled? Well, for the sake of showing how they're copied, that's the primary reason I showed that, Gustavo. But also, you may, if you're in the typical construction of a multi-story sequence, you may run into a condition where the upper floors are actually built prior to the tendons being stressed, and that really only applies to the initial condition where you're stressing the cables and you have to check the stress at what we call the initial or the transfer condition. So at that special case, you may or may not have those upper supports, but for the purposes of checking stress for sustained load and total service load, typically you're checking that with the assumption that the building is in service and you have all the service load on the slab, and in that case you would have the upper supports in place. So there may be a need for you actually to check the stress for initial without the supports, the upper supports, and then check the service and strength, or excuse me, the sustained and total conditions with the upper supports in place. And it just depends on the situation. So thank you for the question, Gustavo. Going back to this, for banded, we're going to use 1.5 inches for the CGS. Allowable stresses, we're going to assume that for sustained and total, the limit is 6. That's just given in the code. That's the hard limit for allowable stress for two-way slabs. If we were working with beams, then this value might float a little bit depending on where we are between 6, 7.5, and 12 square root of F prime C. But for slabs, we'll limit it to 6. And for the initial condition, which I was just referring to, we're going to limit that to 3. And the program, if you have an insufficiency in initial overstress, where you're greater than 3 times the square root of F prime C, the program will add reinforcement for that condition, which is allowed by code. So the way the program does that is if we have just a section, and let's say this is initial section or initial condition, and we have our tension stress here and our compression. This is flexural stress diagram. The program will determine this distance to the neutral axis here. It will take the total tension force over the width of the section. So this, if you think of this in three dimensions, it takes this area times the width of the section to determine the tensile force in the block, and it takes that and takes the n sub c and divides that by 0.6 Fy, and this is hard to draw to write with this mouse, but that is the tensile force that it uses to calculate the rebar for the initial overstress condition. So the program will calculate it, it will envelope it as part of the overall reinforcement for the design of the slab. So the user doesn't need to design that reinforcement. Looks like there may be another question. Oh, okay, that's just a follow-up, so that's okay. All right, for the analysis and design options, we're using, for single level, we are assuming that the base of the columns can translate laterally and also that they're fixed rotationally. So we use a fixed roller condition. There's multiple reasons why we assume this for single level. Let's just simplify it for the purposes of the webinar and say that the reason we're using this is to allow the slab to shorten freely without any restraint. And that can have a big impact on the check for pre-compression in the model. And we actually introduced a new simplified way to check pre-compression in the program because we had a lot of users fighting the axial restraint in a slab and its effect on the pre-compression. So we'll talk more about that in the results when we get to those. So we're using roller support, rotationally fixed. Everything else we're going to leave here as default. I would recommend, we have a document that kind of outlines and discusses, it's maybe 3 or 4 pages, but it discusses each of these different options in detail. If you go up to help, documentation, this document is shown in this folder. So you can access that document, and it's right here. It's called Design Options. I don't know if any of you have used this before, but it's a nice tool to have kind of by your side. It's just a quick reference, and it looks like this. So this is a document that you may want to refer to. Also, while I'm here, for toolbars, we do have a pretty comprehensive document which describes every toolbar and the functions that are used within that toolbar. So those are 2 accessible documents from the program. For loading on the slab, we're going to use pretty simplified loading. We'll use 20 and 40 PSF for the loads, for dead load, superimposed dead load, and live load. So I'll go ahead and select the slab that I've modeled. Under loading, we're going to add load, and we're focusing only on gravity loads for the purpose of designing this for post-tensioning. So we'll add using patch load wizard. The difference between the wizard and just the regular patch or uniform load is that the wizard maps a load to the selected slab region. So the patch load requires you to place points that define the area that the loads are applied. So we'll say dead load is 20 PSF, and again we'll repeat that, and live load we'll say is 40 psf. If I go to a 3D view, we can see the loads are placed here, and if I double click I can review the loading. To show the loading other than having to double click and open the properties for the load, in plan view if you go to reports, single reports, graphical, loading plan, we can report the dead and live or other defined loads that you've created. So if I look, for example, at the live load, this will show just a map of the loading with these dots, and then the magnitude of the load is shown here. So that's one way to view the loads in plan view. Okay, so we have our basic model built, and before we actually add post-tensioning, we can get an idea and kind of a feel of what the deflections are without PT. And this is also recommended, is just to run the analysis prior to adding the post-tensioning and make sure that you have your expectation of the deformed shape, then the magnitude of the shape of the deflections are within reason. There's one more question here. Let me go ahead and answer this. Yeah, can I add perimeter load for cladding? Yes, definitely. Let me do that. So perimeter loading is similar to it's similar to patch loading, and then I can map it, or I can just use line loads. Line loads in this case would take a bit of time because I have to place in between each of these points, but mapping the load would be quite easy. So if we go to loading, add load, line load wizard, I'll assign this as a dead load, and we'll say the cladding load is 500 pounds per foot, and we'll create that, and the program creates individual line loads between each slab points shown here. So that's the cladding load. One more thing I'll make mention of is under loading load combinations, when we select the design code, in this case ACI 2014, the program will predefine several load combinations, and each of these combinations have a specific tag in what they do and how the program treats the load case or the load combination. So anything with a service tag, this means that the program adds reinforcement to that particular combination relative to minimum requirements per code. So if you have a moment and a shear demand for service, the program doesn't design for that demand moment. It designs for minimum requirements for these two combinations. So for example, for a two-way slab, the top reinforcement over a column would be prescriptive depending on the area of the concrete in each orthogonal direction. The program looks at that and calculates rebar per that requirement. For positive bending regions, it's dependent on the stress level in tension. So obviously for total service versus sustained service, total would give you potentially more tension at the bottom fiber in a positive bending region. Therefore, you would have different rebar potentially between total and service, or excuse me, total and sustained. You might have no rebar if both total and sustained are less than the threshold value for stress. You may not need rebar from a minimum perspective based on the ACI code. For strength, there's this other thing here for strength. The program will always add rebar necessary that your Phi-Mn exceeds or is equal to M sub U, the demand moment, and the same thing for shear. For two-way shear, the program designs the shear reinforcement. If for punching shear the stress exceeds the code allowable for, let's say we're using studs, which is 8 times square root of F prime C, the program will report that that condition, that particular column has exceeded the allowable stress, and that's just an indication to the user that you have to do something to resolve that problem, whether it be add a drop panel or a drop cap, change the strength of the concrete, thicken the slab, whatever it needs to be done there, the user would be responsible for that. The question is, does ADAPT have built load combinations for seismic loads? That's a good question. Right now, I'll say this. I think that to generalize the question, can ADAPT produce load combinations for wind and seismic? Okay. The answer is no. The user would have to key in load combinations. However, let me just back up here and show you one thing that can be done. So I'm just going to erase that. I'll save my model, and I'm going to go into file here on my computer. That's if I can find the file. I'm pretty sure I can. Let's see. This is fairly important, so I'll spend a little bit of time talking about this. It could be here. No. Okay, here it is. Yeah, if I can't find this here quickly, then I'll have to just show you just another thing. Yeah, I actually have a version of the software which creates files. So Ted, I'll show you off the webinar what I'm referring to. But ultimately, we have a version of the program which has a load generator, a load combination generator. You put in your loads, and the program will produce the load combinations based on the design code that you have selected. That particular tool won't be released. We have to build out some UI front-end user interface dialog windows in order to support that actual function. So that should be released in version 2017.1, which will be the first maintenance release. But aside from that, let's assume that either you use that combination generator, which is just a direct way to get the load combinations in a model, or if you spend time generating the load combinations, you can see the default list of combos is not extensive. It doesn't cover all of the combinations that might be necessary or critical to evaluate a slab. Especially if you have wind and or seismic loads in a lateral model, you might have 100, 200 combinations. So keying in those combinations takes time, number one, and you also want to have the ability to use those combinations down the road in the future. So what you can do, there's really two things you can do. Once the combinations are keyed in, you always have the ability to store a file as a template file. So I can save project template, and the project template saves criteria, material, and load combinations, or one or two of these three options. If I was to save this particular file, and notice it saves it in this adapt template folder. This is by default located in the program files folder of the software, and this can be moved to a network location so you can share templates across your company. So here I'll just call this webinar template, and if I was to start a new file, and at the onset of building the model, I can actually create a new model using a template. So if I had written 100 combinations in that previous template, and then I come here and use the webinar template, then the file and the load combinations are there for me to use. The important thing to remember is those combinations have load cases assigned to them: seismic, wind, gravity. So you have to follow the same naming scheme for wind and seismic. That's important. For example, if the combination includes EQX and EQY, and you call it seismic X and seismic Y, then you basically disconnect the mapping between the combination and the load case that you're defining in the program. So that's important. The second way to do this is to import an IMP file that contains the combinations within it. So I have a master lateral loading file, for example, that I can use. I'll go to import, generic adapt file. So what I've done is I've exported out a generic adapt file from some other model that I had built all the combinations in, and now I'm re-importing that file back into this model. So I'll just go ahead and navigate to the location of that file. And this is it's called masterlateral.imp. I don't care about any of the components, so I'm going to deselect all of my components. I want to update the model, not create a new model. I'm not going to import load cases. I'm just going to import combinations, so I'll say none to load cases. Combinations, I'll say import all. Say OK, and under the load combos box, I now have 81 combinations shown here. So it takes a little work up front to set that file up, but once you have it, you can replicate it easily amongst other files. Okay, we'll get back on focus here. So we have our model built. We added some cladding loading per the request of an attendee today. We have patch loading and cladding line loading around the perimeter. And now comes the modeling is pretty easy, especially if we're evaluating just for gravity loads. Now comes a little bit more of a difficult part, which is how do we assess the slab for, number one, stresses, pre-compression, etc., based on the tendon input, and that's a function of design strips. So if I was to, for example, analyze this slab, let me just go ahead and mesh the slab first. And I'm not going to talk too much on meshing. I will say node shifting is very, very sensitive. It can lead to differences in results if you're comparing node shift from 0 feet to 1.5 feet. I would never use a node shift size greater than 1.5 feet. What the program is taking nodes, physical nodes, and it's consolidating them into analytical nodes, which one node might represent a physical node of multiple components. So you're from an analytical standpoint, you're creating a substructure which has shifts in it which move the location of the end of an actual component that's modeled in your software or in the program. So my rule of thumb is if my cell size, if I take my cell size divided by 2, and I use that for the node shift, but it should be no more than 1.5. So if it's 3 feet, it's 1.5. If it's 2 feet, it's 1 foot for node shifting. If it's 1 foot, I use 0.5, and so on. And sometimes that might change a little bit depending on whether or not you're able to produce a mesh, but that's something that's important and to keep your eye on. So this is our mesh for the slab. I'm going to go ahead and analyze the slab just for service. This will be just for my service load. I'll turn off the vibration analysis option. By default, the slab is uncracked. I haven't applied any stiffness modifiers to the slab or the columns or the walls. So everything right now is running under the assumed usage case of uncracked. I can add usage cases to the model where I could produce a different result based on applied stiffness modifiers for components if you were wanting to evaluate that. So we'll go ahead and run this. Prior to the discussion on load combinations, we want to run a validation test on the model, again, just to make sure that the deformed shape looks as expected and there's no weird behavior. So this ran. When that runs, the result display settings will open. I'll go ahead and go to my default display to turn off the shell elements because it makes it more difficult to view the results. And you can see in this branched out display window, I'll check the Z direction deflections. So my maximum deflection out on these outer tips of the slab is about 1 inch of deflection. This particular view doesn't really tell me the whole story because I can't warp the view in this main interface. If I turn on the result for deflection here, I can go into my results viewer now, and in my results viewer I have the capability now of showing the deformed state of the slab, for example, something like this, and I'll just make sure that's not as exaggerated. And you can see this is just a quick view to see if there's any disconnectivity between components. Typically, it wouldn't get to this point. You would have received some stability warning, and that would lead you to determining what's causing it. And sometimes that's a disconnectivity between slab and column, slab and wall, or so on. So this looks okay. I mean, 1 inch is maybe not what we want on the tip, but we haven't added any post-tensioning yet. I'll go ahead and close that. And the next step in our process today will be post-tension. Now there's a question here. Let me go ahead and take care of that. Is there a way to change the color composition of the deformed shape contour? Yes, there is. If you look at my contours again, they're green. It's just it's a graded scale, if you will, pink to green. And if you go under settings and you select the option for set colors, I'm using a gradient here. You can also change this to color range and then set your colors, customize the colors here. If I change it to this view and reapply it, then you're going to see it looks like reading rainbow on screen here. So you have a different color scale in this view. Let me go ahead and I'll change that back just because I'm used to the gradient. So we'll say OK and apply. And you can also use the old legacy viewer. If you're not as familiar with this, you might be more used to the legacy viewer. If you go to FEM and select View Analysis Results, this is a little more easily maneuverable for the user, I think. It rotates faster and it just responds faster. So if you go here, for example, select the result, Z deflection, turn the result on, the program will show you the results here, and you can warp this easily. You can deform or warp the actual color contours in this view. So this view is still used. We're actually phasing this out in the next year or two once everything is built in that result display settings, but it's still a useful tool. This is flipped upside down. It should look like this. Does adapt calculate the shortening shrinkage of the slab? It calculates the immediate shortening of the slab due to any axial force, but it doesn't calculate time-dependent shrinkage or creep or other effects that could happen over time. So it will capture the immediate elastic shortening, and both in plane of the slab and also for columns and walls. In this case, if I was to turn on the deformed shape and look at the X direction translation, you can see the columns are actually kind of bowed in at the top. You remember my columns and walls are on rollers. So if I look at this slab, because it's deflecting, it's pulling the slab inward. And if I was to look at the, this is on animation, you can see those moving. But if I turn on the slab actions only and look at the axial stress, you can also view the stress contours for axial stress, and that's NXX and NYY in the two orthogonal primary directions there. So that's, and this is more prevalent once you add post-tensioning, obviously, when you introduce the direct force in the slab due to the precompression of the PT. All right, so in order for us to model post-tensioning, we have to start somewhere. So this is where For those of you who have more experience with post-tensioning, you probably have a better feel and idea of what PT needs to go in the slab. For those of you that might be beginners and just new to post-tensioning, it's harder, especially in a program like Floor Pro. It becomes more of a challenge versus using a program like Adapt PTRC. Again, that will change. It's actually going to change pretty drastic in the next version. And for those of you who are used to the program, I'll show you one thing here. This is the next version of Builder, and similar to the version we're using today, which is version 2016. 2017 requires the user to lay out tendons. You can lay them out just manually. You can lay them out based on mapping. You can send a strip to PTRC and export it back in or import it back into Builder. So assume that you do something to get tendons in the model. And then once you analyze the model and obtain a solution in Builder 2017, in this case, I have a slab which you can see the bottom tensile stress exceeds the allowable. That's shown by these pink regions. That means that the bottom stress, that's the solution I'm showing on screen right now, exceeds the code allowable 6 times square root of f prime c. So in today's version, version 2016, the user has to have some sense of how to approach and fix that problem in the software. So you might have to add post-tensioning. You might have to increase the drape. You might have to do both of those things. You might have to thicken the slab. And it becomes an iterative design process, which can be time-consuming for the end user. And it becomes easier once you have experience doing that, but it's still a time-consuming process. So in Builder 2017, we now have taken this a step further where you have the ability to optimize tendons in a bay, in a selective group of or zone of the slab. For example, this bay along this length in the y direction, roughly you have the same level of stress, overstress in each one of these strips. So these strips that I'm looking at are based on tributary design strips. Here's one tributary, here's another tributary, and then there's a third and a fourth tributary. And when we take and integrate over the length of this design cut for each of these tributaries, we get some moment for the service load combination. We take that moment and we divide it by the section modulus, and we get the stress, top and bottom fiber for each of the sections. And then we end up with this result. So the user can now go in, and I'll go ahead and erase that, and I'll select, turn on my tendons, say, well, I want something, I need a tool that helps me optimize what the tendons should be versus me using educated guessing or doing some hand calculation and modifying things like we're doing today. So now what the user can do is I can go into the tendon toolbar and select this option for optimizer. And this says dynamic tendon optimizer. And I set up optimization parameters. I want the program to calculate the tributary width, and it will based on my selection of tendons. I can optimize based on balance loading, considering self-weight or self-weight plus dead load. The way I report the stresses can either be a ratio, 1 or less or 1 or greater, a factor, which is really the multiple, it's like 6 times square root of f prime c, or the actual stress in PSI. So there's different ways to report the stress. I enter my ranges for precompression, load balancing, and then my allowable stress limits here. And I have now the ability to optimize a selective group of tendons. So let's say I select this group of tendons here. The program recalculates and regenerates 3 virtual design cuts over the selected group of tendons. And those design cuts are shown right here. There's a pink one right at the section. There's one at the midspan. You can see it through those circles. And there's one at the other section cut. and this is now my virtual tributary that I'm optimizing. And the program shows me what the current status is. I have 11 strands selected, or excuse me, 12 strands selected. There's 1 strand per line. The effective force is 27. The CGS is reported. And now I set up my optimizer settings and I say optimize, or I manually override and change different things. I could change total force, I can change force per length, I can change number of strands or CGS, and I can recalculate. And this gives me a very quick tool to optimize certain groups of tendons in any slab in the program. And it also reports the calculation block for the optimization. This is just basically a mirror of what is happening on the back end when it optimizes the span. So this is going to be available in roughly 2 to 3 weeks for anyone that's currently using Builder. It's going to be part of Builder 2017. So I'm showing you the tools that are going to be in place that make it easier to satisfy design. Unfortunately, it's not available today for today's webinar. Let me see if there's another question. It says the sound is off. Give me one moment here. Let me go ahead and see if I can fix the sound. If anyone can hear me and just respond back in the question box, please let me know if you're able to hear at this point. I don't have any indication on my end if I'm having problems with sound. Okay, sounds like a few people can hear it, so that's good. If it does go back off, please let me know and I can switch to a different audio device. Okay, perfect, thank you. So let's go ahead and begin tendon modeling in this slab. So to model tendons, I'm going to use mapping tools to model my banded tendons. So in order to map banded tendons, I have to actually generate design strips first. And if you recall, the design strips that we had wanted to generate for bands were along these few lines that I'm drawing in here. So we have roughly 8 or 9 design strips that we need to create to map the banded tendons. So the design strips that we're going to generate are going to be X direction design strips. They're following the X direction of the main axes, the global axes. So we'll go up here to strips, create my support lines, and a support line is really just a virtual frame line that's used to determine what the tributary region is in the slab. The frame line or the support line should, it doesn't have to touch the slab edge, but if it's inside of the perimeter slab edge, then we have to introduce a virtual boundary, which is called a splitter, that allows us to break out the tributaries. And I'll show the use of a splitter also in the webinar. So I'll start at the slab edge, I'll click on the support, which is a column, I'll go over to the other support, and then just click on the slab edge on the opposite side, and press C to close that, and that's the first support line. Let me just pause for another question. Okay, perfect. So there's more confirmation the sound is working. So let's go ahead and continue here for support lines. Now it can be a little bit tedious to turn this snap to nearest off and on while we're modeling support lines. It's the oval shape of the slab is not too conducive to making this easier because I can't use my perpendicular snap in this case. So one thing that some clients may have a tendency of doing, and I've actually propagated this in the past, so I apologize if this has come back to bite you, but a lot of times what I'll do is I'll start by turning the snap to nearest on, and then I'll just have snap to end point, and I'll snap outside of the slab edge on the opposite side. That's okay, but it can cause an issue with mapping of tendons, a graphical, or excuse me, a modeling issue of the tendons, and I'll show you what that is. We want to preemptively think about how the tendons are going to be mapped to the support line. So in this case, the program will map a tendon span to every span on the support line. So for example, this particular tendon or this support line has span 1, which is this tiny distance here, span 2, span 3, and then span 4. And the tendons map exactly to that same shape. You can do 1 tendon or 2 tendons. We'll do 2 tendons on either side. Or, excuse me, 1 tendon on either side. So in this case, that's fine. The tendon shape might be, it might go straight out and then drop down into a shape, and high point, drop down, and then exit the slab. This is the tendon shape for this line here. But we have to be careful where we have these long walls. So on that long wall that we have below, the tendency might be to draw in a support line that starts here at point 1, point 2, point 3, point 4, and then over here, let's say point 5. And that's fine. However, when we map the tendon, we're going to have a tiny span in between this gap of point 3 and 4. And that just means that we're going to have to spend more time to manipulate that tendon shape, because we're not going to profile the cable over a 5-foot span. We're just going to run these cables just straight because it's a continuous wall. So there will be no drape in the cable. So we want to make sure we preemptively think about things like that when we're setting up our support lines if we're using the mapping tools. There's a question. Is there any way to mimic a slip joint connection between the wall and the slab? Why am I, and then there's another question, why am I running a band over the wall? Well, we don't need any drape in the tendons over the wall, but because it's a two-way, let's say a two-way PT slab, obviously if we have a continuous wall, then at and near the wall it actually starts to behave one way, but we're adding tendons here to pre-compress the slab over the wall. That's the only reason that we add the tendons, is just simply to provide pre-compression in a zone that might be, from here maybe out to here. In this zone, we want to add pre-compression to the slab in that particular region over walls. So we just run those straight through. Again, there could be an argument that near the wall the behavior changes to one way, but we're still designing this as a two-way slab. There was a question, can we add a slip joint over a wall? If we click on the wall and go to release, we can release the translation and the rotation between the wall and the slab using this release option. I think that answers that question. If not, I'm maybe thinking differently than what the intent is there. Just let me know. So let's go ahead and continue with this support line. So I'll go ahead and, instead of going point 3, 4, and 5, I'm just going to run this all the way to the opposite end and stop that support line. If I zoom in, notice that it doesn't extend to the end of the slab edge, so I'll just drag it out to the slab edge. That would actually cause a problem in generating our tributaries had I left it like that without a splitter modeled. So, and the splitter, again, we'll talk more about that. Now I'm going to start modeling this a bit faster. So again, here there's another gap. There's actually some link beams in between these walls, but I removed them from the model to simplify what we're covering. So this is our next support line. Let me backspace. Okay, and then we'll start outside, run all the way to the end. This is, again, this continuous condition. So we have our banded support lines. If I generate design strips now, this is the second step in the process of generating the banded tendons. I can go to strips, generate my design sections manually, and regenerate the tributaries. So this will generate both the tributary regions that are linked to these support lines and also the design sections that are cut perpendicular to the support line, which are essentially data points in the slab that give us moments, shears, axial force, and stresses, both axial stress and also flexural stress. There's a question. Tendon inside a wall is not going to work because of the stiffness of the wall. So usually I've heard the slab is separated from the wall until post-tensioning is done. Should that be modeled in ADAPT, and can that be modeled? So you're talking about the restraint of the wall. It's apparent that the wall, if the wall is tied to the slab prior to the post-tensioning being stressed, you're going to lose PT down into the wall because the slab can't shorten, so you get a restraint issue. So the program inherently considers the restraint of walls and supports and boundary conditions. If, for example, I'll kind of highlight it next. If I have a slab that looks like this, and I have a wall here and a wall here, and on the outsides like so, and I put PT in here, and I stress this slab, and these walls are locked into the slab, then you're going to get cracks all over the slab because of the restraint. So the slab has to be detailed in real life in order to mitigate the loss of precompression due to restraint, and also just to mitigate the fact that the slab is going to crack, or the wall might crack due to that stiffness of that vertical element. The program will consider that in its analysis. If you modeled this arrangement here and you fix the base of the walls and you didn't release them from the slab, and you ran the model and looked at the axial stress along these strips, you're going to see losses in axial force at the walls. So the way we check the precompression in the slab, we can check the precompression based on the FEM method, which considers that restraint. And if I go to the red eyeglasses, this is my result display settings, you'll notice that there's two options for precompression, FEM or number of tendons. FEM considers the axial force along each of the sections within a strip, and if you have wall restraint, that axial force will consider the fact that there's restraining components in the model. If you check it based on number of tendons, we ignore the restraint, and we take the number of tendons, divide that total force by the section, and give you the precompression. So the second option just basically ignores the axial buildup in the slab, or loss of precompression in the slab, I'll say, and it checks the precompression, assuming that outside of the model in your detailing you take care of the restraint issue. So that's why we have two different options here. We had so many people using the first option and they were fighting the restraint problem, but in reality there's no real great way to mimic your release detailing in the program. You can mimic it somewhat, but there still will be migration of force into the walls if you have walls modeled in the software. And to avoid that, we went with the second route and we added this simplified option. The simplified option is the same thing you do by hand when you're checking precompression, or it's the same thing you might do in a 2D program like ADAPT PTRC. We don't consider axial restraint or deformation in the plane of the slab in that program. We just throw it to the side and say, this is something obviously that you have to consider, but it's not part of the methodology implemented in that program. So Hopefully that answers that question. Okay, so I realize there's been some discussion on adding tendons near walls. We will add tendons near walls. Obviously, it's a judgment. If you feel you don't want to add tendons near walls in a real design, that's up to the discretion of the engineer. But we've seen it done both ways. So we'll add tendons to this zone of tributary for pre-compression purposes, assuming that we're going to have detailing that considers and allows the slab to shorten. Okay, so let's go ahead and generate our strips. So I'll go to strips, generate the design sections, and I'll generate these design strips. And you'll notice there are colored regions that are our tributaries. And we have 1, 2, 3, 4, 5, 6, 7, 8 tributaries in the program, in the model. So each one of these tributaries we're going to use now to map tendons as a starting point into the banded direction. So I'll give you an example. I'll just take this tributary here to start. I'll go ahead and under my tendon toolbar, let's turn off these other toolbars. I'm going to use the fourth icon, which is to map a banded tendon. And that opens up this interface. And we're going to use the design strip width, which is this, just the width of each of the design sections, to determine the required force to meet P over A and balance loading and so on. We'll enter the range of pre-compression and max and min pre-compression, so we'll say 125 to 300. And I know some of you may use different values than that. The minimum is typically 125 or maybe 150 conservatively for a two-way slab, just depending on the design. For balance loading, we'll say 50 to 90. So the program uses this input to optimize and place, or let's say calculate the number of strands needed to meet this particular zone or tributary. There's a question, I'll go ahead and answer that in just a moment. The placement of the tendons can be done three ways. You can have the program output every individual tendon spaced at some increment over that tributary, or you can idealize the tendons. Let's assume we need 20 strands, 20 half-inch diameter, 270 KSI tendons unbonded, we'll assume, in this zone. Well, I can either model every single individual strand, so we'll have 20 of them, or I can say I want one group of 20, two groups of 10. There's not a huge difference in terms of stress and overall behavior if you model them as representative groups. You can get differences in deflection. So if you have, let's say, very sensitive deflection requirements and you need that to be very, very accurate, then I would recommend modeling on the side of more tendons versus representative groups of tendons. So in this example, we're going to use two groups of tendons. We'll use idealized as two groups, and we'll offset this 1 foot each side of the support line. The effective force we're going to assume per half-inch diameter strand will be 26.7. That's roughly, well, it's directly calculated as 175 KSI. That's our final average effective stress we assume times the area of the strand, 0.153. That's that value here. And then for the shape, the first span is this tiny little span on the end. So we'll say that's really a cantilever down shape. The mid span, which is spans 2 and 3, are these two spans, and the last span is the other cantilever on the opposite end. And we'll say cantilever down for that shape. Say OK. And the program adds two tendons to the slab. So let me take pause and answer questions. Yeah, the question is, can I show the drawing of the splitters? Sully, I'll show the splitter modeling when we go to the the Y direction. If you can wait about 5 to 10 minutes, I'll show that. Okay, so we have these tendons that are developed in the slab. The tendons, and when I say literally, I mean literally, they follow the shape of the support line. So you can see this tendon is actually outside of the slab, this one's inside, and that's because I was a little bit sloppy modeling the endpoint of that tendon. That's not to say we can't easily fix that. I'll just select the tendons. Under the tendon toolbar, I'll use a trim and extend, and it trims back the tendons 3 out of the 4. This extension is too long to trim back. In the new version, you'll be able to easily change that extension threshold, but in this version you have to go into an INI file to modify it. So I'll just drag it back to the edge of the slab. And if I double click on one of the tendons, this is representing 5 strands, so a total of 10 for this strip, necessary to meet the balance loading and the pre-compression that I set up. The stressing is based on effective force method at 26.7 kips per strand. Location just defines the geometric position of the tendon. We'll just leave that alone. The shape of the tendon is shown as such, and you can see it assumes that CG value of 1.5 from top and bottom that we set in the criteria. However, in span 2, it actually lifted it by 1/2 inch to maintain the balance loading range that we had specified in the optimization input. So makes that adjustment for that tendon. And if we need to make any changes, for example, if we say, well, this is a pretty steep drop over 2.3 feet, you can go in and make changes to the CGs for any of the spans, the inflection points, and so on for any tendon that was mapped. Once it's mapped, it becomes disassociated with the mapping function. Now it's just a tendon as if you drew it in the slab. So so you can modify any mapped tendons. And so if I take all of these strips, and once I show the mapping and how we're going to model the distributed, we'll go back and I'll use the model that I've already set up in the program. But I can select all these at once, go to the option for mapping. I'll use the same criteria. The program then adds all of my tendons. Now, we have several tendons that are outside of the slab, so I'll just comprehensively select everything and use the trim extend tool. And there's a few that it didn't trim extend, so I can take those and draw those back to the edge of the slab. And so on. So you would make that change for all the tendons. If you leave the tendons out of the slab, because of how we treat tendons in terms of the solution, we have to make sure they're in the slab. They can actually pass through an opening, but they cannot be beyond the outer perimeter of the slab. Does the program track material quantities, footage of tendons in the model? Yes, it does. There's a quantity report. So, for example, if I was at this point, because I have these modeled, if I go to reports, single tabular reports, I could go to tendon report. This gives me length, shape of the tendon, and so on. This isn't really a quantity report for PT, but it does give you additional information for PT. If I go to the quantity and cost report, this would produce just a Word document, and you can see right here there's a pre-stressing material summary with quantity. This is just some default cost relative to the material assignment, and this itemizes it for each of the different materials. So there is a way, and then this gives me more information for tendons, diameter, strand area, total strand length, and so on. So this quantity report is helpful in that respect. Now the uniform direction. So this is basically our starting point for banded tendons. The uniform direction is can be done multiple ways. One way is to model a slab banded. So you actually set up design strips in the Y direction, and you map tendons to those strips also, and you run a banded design, and that is advantageous to do that if you know, in terms of time. It just is easier to do that. It's quicker, and it sometimes requires you to go back and expand those tendons out into uniform tendons, especially if, again, you have a sensitive deflection problem. But it can be done. You can use a banded system. The question is there a specific reason why you model the banded tendons in the short direction of the building? Generally, uniform is in the short direction, reduces the triangular unstressed area between bands. Yeah, it was just arbitrary. I understand the differences between, you know, uniform and banded. This is an actual design that has been done. It's a building in Chicago, I believe, and in the actual design that was done by a firm, they modeled banded tendons in this direction. So we were running a comparative design in Builder for them, and we had to keep the same tendon direction. So that's the only reason why we did that. But I think Kevin is talking about if you have banded tendons and you have a tendency to get, you know, these triangular zones where you don't have pre-compression, and then you're required to go in and place rebar along the edge of the slab because of that zone that's unprecompressed, and it's more advantageous to have the uniform cables in the long direction, or perpendicular, let's say, to the long direction versus the banded cables. So the banded might be in this direction to reduce the distance between that area where you have that triangular loss in precompression. Okay, so for the uniform direction, we have to make a decision on how we want to model the tendons. We can map uniform cables. The shape of this slab is not conducive to mapping. Mapping of uniform tendons would require a slab that it doesn't have to be perfectly square rectangular, but if you have rectangular zones in a slab, then you can use the mapping tool. So for example, if I had a slab that was shaped like this, and let's say my banded tendons are this direction, my uniform are in this direction, in this case I would draw a master tendon in the uniform direction. So that's just a manual input of a tendon using the add tendon tool. And then we would map, if there's 1, 2, 3, 4, 5 points that define the high points and the anchor points of that tendon, we map those 5 points over some range that master tendon would apply and its shape. So in this case, the range, we would map it to point 1, 2, 3, 4, 5. The program would then fill in tendons in this zone. So this is how the uniform mapping works. And then we would draw another master tendon and map that over its given range, which is to here. And then draw another master and map that over that range. Now, that's not necessarily the best way to do a slab that might be conducive to using the mapping. A lot of times, clients will just simply space tendons at a given spacing, and knowing what that spacing is, you can easily determine how much force you need necessary to meet, let's say, pre-compression and maybe balance loading. You can determine the drape necessary to meet the balance loading. That could easily be done in a PTRC model that you bring over to Builder in terms of the profile and force. And then you would replicate that tendon over some set spacing. If you look at the model that I have on the other screen here, let me go ahead and erase that. In this model, well, let me go to, there's a third model. I have 3 models I'm juggling here. So under webinars, Floor Pro, we're going to open the model with tendons. We'll save that model. So in this model, you'll see I have the bands in blue. Those are actually turned off right now. They're being disregarded in the model. But I have set tendons every 4 feet. So from this edge over to here, these tendons, this is 4 feet spacing in between the tendons. And then from the core, kind of the extent of the core from here over to here, these tendons are spaced at 5 feet, technically 5.09, but just say 5 feet, and then 4 foot spacing again. And then on the perimeter, I have 5 strands that kind of wrap around the perimeter of the slab. And so I keep my spacing as is, I keep it set. And then if I find that I need to add more force or more tendons necessary to meet, let's say, allowable stresses or pre-compression or whatever it is, I can slide or reduce the number of cables at that spacing increment. So I'm not adding cables, I'm not having to track both number of cables and spacing, which happens a lot of times if you use mapping. You have to know both in order to transfer the final, the final design from this program to your drawings. So I keep my spacing consistent, and then I'm just worrying about the number of strands. So that's how this has been modeled. Now, an alternate way, again, as I mentioned earlier, was to use banded. So in order to do that, we have to generate design strips for the uniform direction. Now, typically, the support lines for banded directions will follow the actual flow and the location of supports. For uniform tendons, because we assume the bands are basically virtual supports for the uniform cables where we're distributing load from uniform to banded, we don't technically have to follow the line of the supports. We could go in here and actually model uniform, let's say, support lines across the width of this model for our uniform tendons. But in this case, we're going to use mapping. We'll map banded. We'll model the uniform as banded lines. So we have to have some support lines to do this. So the support lines that will follow look similar to this model, and I'll turn on the. Let me turn on the strips here. So this is Y direction, and you can see the support lines that I've modeled. Now in this case, I'm not going to, I'll use this model at this point. In fact, let me switch over to this model here. Okay, so in this case, I've had to introduce these things called splitters. If I turn the splitters off, you can see the splitters are these blue lines that I have snapped to some of these support lines. I'll turn the splitters off, and I'll show only my support lines. And my support lines look like so. This one actually I need to remodel this one and the outer one here. So let me just do that. Because I have a support line which wraps around the perimeter, these need to be modified. So I'm just selecting this and deleting some of the points. The reason I'm deleting these points is I can't have two support lines that are labeled Y direction intersecting one another. So I have to terminate. They can share a common point, but I have to terminate one of them at that common point, and the other one can be continuous. So that's the purpose of me deleting these points on these support lines. The continuous line will be on the perimeter, and then these will stop at that line. So let's do that. So I'll go ahead and introduce a new support line. This will be in the Y direction, and I'll start that support line here. This is just some cantilever off the edge of this, or the end of this column, and then this support line will just wrap around the perimeter of the slab on this side, and I'll do the same on the opposite side. And maybe we'll stop that there. And because I'm mapping my uniform cables to these strips, then I have to follow essentially the shape of what my uniform cables I want them to look like. Now that may be slightly different than how they're actually represented on plan. So again, there's more ways than one to do uniform cables. We're just showing you a map, a banded arrangement of the cables here. So we have several conditions here where we need splitters. And by the way, the time, we've gone basically up to the allotted time, which is an hour and a half. This is being recorded, so if any of you need to exit the meeting, please feel free to do so. I'll probably go another 5 or 10 minutes, and we'll likely need to schedule a remaining session for this this topic. It's a topic that we typically take 2 or 3 trainings for clients, and I'm trying to cram it into one to 2 trainings here. So please feel free to go if you have to, and those that wish to stay, I'd be happy to continue here for just a few minutes. So we have conditions where we have to introduce this thing called a splitter, and the simplest way to locate the start point, or let's say the location of a splitter, is if a support line's start point or end point is within the perimeter of the slab. The easiest one to show here would be this support line here. The start point is obviously not extended to the perimeter, and nor is the end point. So when the program is breaking out the tributary for this condition, this support line, it shows a support line. There's a support line here on the left, there's one over here on the right, and it knows that in the X direction, to break this into half the distance, we'll call this distance L1, and then this distance, let's say, as L2. So it knows to take L1 over 2 and L2 over 2, and then this becomes the tributary for this strip. But it doesn't know how far to extend, where to bound that tributary off at the top and the bottom, because there's no boundary. If there was a slab edge here, then it knows, oh, we'll go up to the slab edge and stop. But there is no slab edge there where the support line stops, so we have to give the program some guidance in the form of a splitter in order to allow it to break the tributaries up properly. And so for this condition, we're going to add a splitter. We're going to add that virtual boundary just straight across. That's where we want the tributary to stop for that particular region, and we'll do the same at the bottom. And so I'll go up here to strips, create a splitter. Now it's important to note that the splitter needs to be labeled as the same direction as the support lines that it's being used for purposes of generating the tributary. So this is a Y direction splitter. Even though it's oriented in the X direction, it's still called a Y direction splitter. So I'll take this, I'll start it at this point, and I'll go to the left side. I'll terminate it at a slab edge or at a continuous support line, whichever comes first. That's the basic rule of thumb. So we'll stop it at this support line, and I'll do the same thing there. There's my virtual boundary, which stops the tributary, and we'll do the same thing on the opposite side here. So that's the first location of a splitter. Then we have a little bit more of a fuzzy location, which is not apparent just looking at this, but these line, this point, and this point, and then the 4 on the opposite end, these terminate at this support line, which is kind of going around the edge of the slab. And so we have to be able here also to generate tributaries, and so because this stops on the inside of the perimeter, we also have to add splitters. So I'll go ahead and do that, and we'll go to strips, splitters again. This is already set to Y direction. So here I'll start here where this line terminates. I'll go to the continuous support line to one side, And on this side, there's a slab edge, so I'll go to the slab edge here on this side, and then I'll do the same thing here, like so. By the way, this needs to be extended up. If I didn't extend that up, then I would have needed a splitter, and then I'll readjust this splitter because I moved the support line that was snapping to it. We'll do the same thing. Let's see, we'll go over here to splitter. And do the same thing on the bottom side. Okay, so if we look at how the program, theoretically, how it should break out the tributaries in this zone, the tributary for this support line right here should look something like this. It would split it from this splitter up, so this is half goes to here, half goes to this one, and then it should split this kind of on a triangular basis. Half goes there, half goes there, and then it would split it, you know, again on a triangular basis here, and so on. So that's how we would expect this the tributaries to come out here. There's a question. Do we need to draw splitters around openings? I'll end with that topic solely, and I'll use that as a question for the question-answer period at the end. So sorry to put you on hold again, but give me just a moment to finish this, and then I'll answer that question. So let's generate the strips here. We'll go to strips, generate, and we'll regenerate the strips. And I get like colored tributaries everywhere and design sections. So this looks a little bit messy. I'll go ahead and just clear the screen, and I'll look at only my Y direction. And this shows me the support lines. So these are the support lines we're going to map tendons to. Similar to how we mapped them for banded, we're going to map them also for uniform. And that we'll do that in the next webinar that covers that topic. But what I wanted to show was, to show this a little more clearly, I'll use my graphical reports again for my design plans and design strips in the X direction. And this shows us the breakout of the tributary. So you can see that kind of sawtooth pattern on this outside that's based on how we generated those support lines. And these strips look like we would expect based on the generation of the support line. So, and the splitters. But that is the set of design strips that we will use for the uniform direction. So at this point, because of time, we'll go ahead and conclude with just questions, additional questions. We will schedule a second webinar to finish this, to add the distributed tendons and go through some results and processing of the slab and the design and analysis. I apologize for not being able to get through everything today, but there were some topics that were important to discuss as well. So we'll open it up to questions. I'll go ahead with the question that was just asked about the splitters at openings. So let's go back to the view of design cuts in the, let's see here. Let me generate the strips one more time. Okay. Oh, I'm still in report mode. I was wondering why that wasn't happening. So, okay. So in this case, I'll show you a couple of conditions. If a support line enters an opening but doesn't exit out of the other side, then you don't need splitters at the opening. This is an example of that. This support line comes along, there's slab, 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 and then it goes into an opening, and then we're done. There's no slab that it cuts beyond that point. So it basically ignores this zone right here. And the same thing happens from the other side. It enters an opening, but it doesn't exit out of the opening on the other side. So that does not require a splitter in that case because, again, there's no concrete in that opening that it can gather results from as part of the nodal integration process. In the other direction, let's see if we can find. So like right here, we have an opening that's right there. This support line goes into the opening and it also exits the opening. So what happens in that case when the program calculates the design section actions for that slab, basically what it's doing is it's taking a slab here, and then we have this opening, and then it has a tiny portion of slab over here, and it's taking those two pieces of slab and it's converting it into one solid slab. But in reality, you have a discontinuity. And so when it calculates reinforcement and it checks stresses for this section, it assumes that it's a combined section, and it integrates the nodal actions for shells or frame elements representing these slabs, or in some cases beams, for this design cut, which can lead to an inaccuracy in the result. So in that case, we would want to have a splitter, and I'll quickly show you. If I go back and just turn off and discard my design strips, I'll turn on the current set of splitters for the Y direction, and I look at this and I say, okay, I need to add a splitter here. And what I want the program to do is I want the program to take the tributary for this support line right here. This is the two sides of the tributary, and I want to take it and push it over to this face and then come back down. So the tributary kind of bumps out along this side, and the section cut is continuous all the way to the face. And on this side, the section cut basically comes to here and stops. So what we'll do is add splitters. I'll go back to my create a splitter tool, and I use the corners of the openings because they're easily that you can easily snap to them. So I'll go from here to there and over to the support line that's continuous and stop. I'll go from the same point to this support line, and we'll do the same thing on the bottom. Okay, now that doesn't help. These are useless at this point because I need to tell the program what face. I need to tell the program that the face of the opening stopped the tributary. So I'll put a splitter there and a splitter on this side as well. And this one needs to be readjusted. It's in the wrong spot. So I basically have splitters over on all four sides of the opening and extended from the corners out to the continuous support lines adjacent to the region I'm trying to split off. So now the program sees this. There's a support line. It takes all of this tributary because it can't distribute anything to this support line because this is blocking it, the splitter. And so the outcome that we outlined earlier hopefully is shown here with this support line, and there's the way it has created that. So now this stops at the face and this stops at that face. So hopefully that answers the question. Any other questions? I'll just wait 2 or 3 minutes here to see if any questions come in, and I'd be happy to answer those for you. Okay, doesn't look like there are any other questions. If you do have questions, please feel free to contact us. Just as I say that, one more. Okay, go ahead. It looks like there's one more question. The question is, if we're doing distributed tendons, do we not need support lines? We still need support lines in order to evaluate the stresses in the slab in the distributed direction. So if I go back to my model that has tendons, let me open that. I'll save this model. If I go back to this model, and I think I have a solution here, let me just check. Yeah, so you'll notice I have my distributed tendons. Actually, they're the only ones active in the model right now. I was checking balance loading kind of separately in both directions. And in order to get results along strips versus just contour results for, you know, stress and pre-compression, we're using representative design strips along frame lines or unit strips for a uniform direction to generate a result and check flexural stress, pre-compression, balance loading. So in this direction, you can see I have strips that are set up that allow me to check those different criteria necessary to meet an acceptable design for a PT slab. So, for example, I have balanced or bottom flexural stress for the service total condition. This shows the distribution of the stresses, the bottom fiber stress along strips in the uniform direction. So in order to check it, the slab in this way per strip method, you must have the strips defined in both directions essentially. All right, well, I will conclude there. I appreciate everyone's attendance today, and again, the video will be placed on our YouTube channel, youtube.com/adaptsupport. And if you have any questions about the meeting, please feel free to contact us at support@adaptsoft.com. Each of you will be sent an invitation to round 2 of this webinar, and we'll likely conduct that not this coming weekend due to the holiday here in the US, but the following week in September. So I appreciate it. Thank you.